Hi guys, I'm Farah from Guitars AI and I welcome you to this Python tutorial where you are going to follow the steps of Pythagoras and his observations and studies about the different ratios of string lengths of the Greek lyra and how we went from there to the diatonic scale and the chromatic scale that's used nowadays in Western music. So there are many legends surrounding Pythagoras and his music and mathematics studies. There is a famous one in which he observed and experimented with hammers. One day he saw a blacksmith hitting with different hammers and that were making different sounds, and he experimented with that and he came out with ratios. The thing is that the physics behind it is not really working with hammers, but his ideas in another legend that he was studying, he wanted to study Greek music, and he started to study and observe the ratio between the lengths of strings in a lyra. So and these ratios, they stand, the physics behind it stand, and we can use some standing waves equations in a string to fundament this thinking. Anyway, Pythagoras was a genius, a mathematician, philosopher, and his contribution also in music is phenomenal. So let's get started. As usual, I'll import the packages we're going to use. So I'm using the Music21 library to handle musical notes and pitches. Display, Python display and image, and these functions, you're already familiar with it if you're following other videos. That is to display the musical score generated by Music21. I'm using librosa to handle audio and to some auxiliary functions like to convert hertz to notes, notes to hertz. And this time I'm using sympy, just for you to have a feeling how to use symbolic mathematics and how to use Python to the very basics of equations manipulation. So before we go into the studies and observations of Pythagoras, we need to go over the string vibration and the string and wave equation of standing waves in a string. So you'll find in many different books about this subject. This is a common equation in which the frequency is a function of the square root of characteristics of the string and the tension applied to the string and the length of the string. So the fundamental frequency is the square root of the tension divided by the linear density, which is like mass per unit length. So here is where the gauge of the string and the material, what is made, will influence. The tension is like newtons, the strength you're tuning your string, and the length of the string. So this is a fundamental equation that we will use to fundament the observations of Pythagoras. Yeah. One thing to notice is that Pythagoras was working with ratios, and when we use ratios, it simplifies a lot, because if you consider the same string with the same tension, and we take the ratio between, then just the length will influence the frequency. So if we have the same string with the same tension and two different lengths, this will influence the frequency it produces. And when we take the ratio, so we divide this equation by this equation, and we here I'm just defining the symbols I'm going to use in sympy. Here I'm defining an equation. This is how we do it. So it's this one. Now I'm defining this and this equation, and the equation 3, I'm just dividing the left hand side of the equation and equals to the right hand side of the equation divided. So sympy already simplifies because this is the same. So the only difference is so it's f1 divided by f2, and then it will be this cancels with each other, and then it will be the length 2 divided by length 1. And then we have this equation, and if we solve for f1, this is what we're going to do this. So the f1 is the length 2 times f2 divided by the length 1, and this is a ratio that we're interested at. So what Pythagoras did, that he used the same strings, and he started to observe and to listen to the sound produced by strings with different lengths when you have the same tension applied to it. So one way we can think about this is like in a guitar. So we have here a string, and it's tuned with the tension, and there's this length. And if we move our finger here, which would be the same as moving the nut to here, now we are half the way, the same string with the same tension, and we will see that this and this, we have an octave interval. Well, Pythagoras experimented and made different tests with different ratios, and in his experiment, first thing he found out is the unisono. So if you have the same string with the same length and the same tension, the sound will be the same, and it's very pleasant to the ears. Another interval that caught his attention was this 2 by 1. So when a string is twice the length of the other, it produces a sound that we call it octave. And in his observations, he thinks it was a very pleasant sound for the ears. So in fact, it was so pleasant that he decided that it should have the same name. This note should be the same, just it's in a different octave. So here, for example, we're just defining a note, which is the D3. This fundamental frequency is 146. If we substitute in this equation, and we consider that the length of the second L2 is twice of the first one, so we have this ratio of 2 by 1, we will get a D4, which is twice the frequency of the D3. So now I'm just using librosa and sympy. I'm just substituting the values here into this equation, just to show that the ratio 2 by 1 will produce an octave. Okay? He experimented with different ratios, and some ratios he found out that it was very pleasant to the ears, like the octave, for example, and some were not so pleasant. And after the octave, which is the ratio 2 by 1, he was very, very impressed with the ratio of 3 by 2. And he said that after the octave, this was the most pleasant interval of all in these ratios. So again, if we substitute into this equation and we put a ratio of 3 by 2, we started with a D3, and we calculate according to this formula, this equation, the ratio of 3 by 2 will give an A3, which is the perfect fifth of D. So Pythagoras had this idea. He would just use this, his boundaries would be 1 octave. So the string would be the ratio of 2 by 1. This is his limits. So it's from D3, for example, to D4. And he wanted to use different ratios and see what would come out of this experiment in his attempt to study Greek music and find notes that are characteristic to this kind of music at the time. And then he decided to use the perfect fifth, because for him it was the most pleasant interval, and it was given by this ratio of 3/2. So what he did was, he started with D, for example, with a note, and then he would make a ratio 3/2 and 2/3. So he goes a perfect fifth up and perfect fifth down. Every time this new note generated by this ratio was outside of these boundaries that he decided, he would just shift by 1 octave, so multiply by 2 or divide by 2, in a way that it would be always be inside this this interval, these boundaries. So here I'm just doing this is a function that will take a pitch, and it will define this boundary, which is a 1 octave, so it's a ratio of 2/1, and then it will calculate the perfect fifth, which is the ratio of 3/2, up and down, and every time it goes out of the boundaries, it transposes to the octave, so it gets inside these boundaries. So we have here this function. There's the forward, which is I'm transposing forward, so is the fifth, and then a fifth backwards. So we have these two sections here. So